The MetaQuest browser is a powerful and flexible platform for immersive XR experiences. Open standards like WebXR, WebGL, and GLTF enable developers to create and deliver high-quality XR apps, and only a hyperlink is needed for users to start using your app. However, for a developer, the tools and processes needed to build amazing WebXR experiences are different from the tools used to make most native XR experiences, and also different from traditional flat web authoring tools. I'm Scott Nagy, a developer on the MetaQuest browser team, and I'm going to share what we think are some fantastic tools to supercharge your creation of great WebXR experiences. I'll also be talking about an immersive case study WebXR experience that we've built to showcase how to create high-quality WebXR apps. We're calling this experience Project Flowerbed. Here's a quick peek of it running in the MetaQuest browser. We're releasing a preview version of Project Flowerbed today, and you can load it up in a WebXR-capable browser and try it out. The QR code that you see has a link that will take you directly to the app. Later this year, we're going to open source all of our code and content that went into Project Flowerbed, so folks can explore what we've done and learn from it. We're also planning to release a more polished version of the app later this year. Okay, when we want to build something like Project Flowerbed, how do we do it? Today we're going to cover three key aspects of developing a WebXR app. First, what engine should we use to build this? Then, how do we create and process our content? And finally, what tools are available to help develop and polish our WebXR app? The first question most folks have when they start a WebXR project is, what engine should I use? Sure, you could write all your WebGL and WebXR and physics and whatever code from scratch, but if you're like most developers, you want to leverage an existing engine to accelerate your development process. For Project Flowerbed, we chose Three.js as our core rendering engine. Three.js is an open source Web 3D engine that has a huge community that has created a vibrant ecosystem of different components which layer on top of Three.js to provide things like physics, AI, or even path tracing and advanced rendering in any browser. Best of all, Three.js has first-class support for WebXR in the engine, which can be activated with a few lines of code. We chose Three.js for Project Flowerbed because of its flexibility as well as its community. Because Project Flowerbed is a case study app for WebXR and the MetaQuest browser, it was important for us to build on top of a community-driven engine like Three.js so that we could really understand how other developers are building their experiences today. Three.js isn't the only WebXR engine option. Some other engines to consider include Babylon.js, a TypeScript-based engine that comes with some cool built-in tools like a scene inspector, or PlayCanvas and the Wonderland engine, which both offer editor-based workflows similar to traditional game engines. Unity also has an option to export a project for WebXR, which is a good way to get existing content from Unity onto the web. The web-based engines like Three.js and Babylon.js are flexible and powerful foundations for WebXR apps because they're written specifically for the web platform. They integrate well with web development tools and workflows, and are focused on efficiently packaging and distributing content and code over the internet. Getting back to Three.js and how we used it. Three.js is built for the web and focused on rendering, and is designed to be composed with other modules to deliver the specific functionality an app needs. You can either assemble these components piece by piece, or use a framework which provides a more complete set of functionality to build an app. A-Frame is a popular framework which adds a fully declarative structure on top of Three.js. This lets you author HTML-like content that shows up as a 3D scene and provides an easy way to immediately arrange some 3D content and display it in WebXR. React 3 Fiber is another popular option, which wraps Three.js as a React renderer, enabling developers to interface with Three.js through React components. This creates a really familiar environment for folks who are already experienced working in React, so they can start authoring 3D web content with the same paradigm. For Project Flowerbed, we decided to compose our own set of libraries together instead of using one of those frameworks. Because Project Flowerbed is an exploration of the 3D web ecosystem, we wanted flexibility to kind of mix and match pieces as we built it. For example, we want to use an entity component system architecture to organize our project in a performant way. So we use an open source ECS implementation to manage our objects and application-specific behavior implementations. To drive our physics and raycasting, we grabbed 3-mesh BVH, which implements a bounding volume hierarchy on 3 meshes, and gives us fast collisions and raycasts. And then we wrote our own layer on top of that to define interactions and responses to those collisions. We also used other components to help manage our custom materials, render immersive UI and controls, and run our positional audio system. These libraries all layer on top of Three.js and kind of let us compose our own custom engine and give us a great foundation for our app. Now that we've decided on our core technologies, we need to start getting some content to put into our app. Here's DM Liao, another engineer on the MetaQuest browser team, to talk about the content creation tools and pipelines we used.
Okay, now we have an engine and need some content. But what content exactly? You need some visuals for one, 3D models and textures, and you'll want some audio too, sound effects and music to make the experience more immersive. I'll go through all those in time, but let's start with the 3D models because that's the vast majority of the content you're going to need. For Project Flowerbed, we use the GLTF file format to save our 3D models. The GLTF format is an open format that was designed to be the JPEG of 3D and is strictly a delivery format, optimized for small file size and fast runtime processing by applications that use them. It enjoys out-of-the-box support on all the engines we talked about earlier, and most of the engines have viewers available that enable us to quickly see how our models render in-engine. Here's the same Squirrel GLTF from Flowerbed across GLTF Viewer, which was built on Three.js, Babylon.js's Sandbox, and PlayCanvas's Viewer. The GLTF file format also contains a wide array of features that are useful for developers. Nodes, transforms and scene definitions, full PBR materials, skinned meshes, and morph targets, and if the core features aren't enough, it also supports extensions for custom needs. More material features like sheen and gloss, compression schemes, GPU-ready texture compressions, among others. And speaking of material features, Kronos' 3D Commerce Working Group is building GLTF extensions designed to enable more realistic and accurate materials for product renders. So great, that settles the model format. What about textures? They're just images, so you can use PNG or JPEG, right? Sure, you can, but we recommend using the KTX2 texture format. It is a texture transmission format that is specifically optimized for delivery and transcoding for rendering on the GPU. It's got a lower memory usage than PNG or JPEG at runtime, but a similar file size on disk. That means you can fit more textures into your GPU and also render them faster because they render from a compressed format instead of the raw RGBA that PNG and JPEG have to expand to on the GPU. It's also got tunable compression support, of which there are 2 main types. The ETC1S mode is higher loss, but much lower file size, and the UASTC mode is very high quality and a higher file size to match. And regardless of which one you use, you can compress them even further with gzip. And so if there's anything you should take away from this talk, it's that KTX2 textures are great and should be incorporated into your asset pipeline if at all possible. Now that we've got the file format settled, how do we make all those models? There are a number of tools available, but for Flowerbed, we used Blender. Blender is a 3D modeling program, and it's free and open source, and natively exports the GLTF. We used it for everything from authoring individual objects to creating the entire environment for Project Flowerbed. Blender is very flexible and allows you to do a lot of scripting, which also let us use it as our level editor. We assigned custom properties to individual meshes from within Blender, which allowed us to attach JSON data directly to the nodes in the GLTF model, and then read those properties in engine later to attach gameplay behaviors. So things like where ambient sounds would play, where to place props, which objects have colliders, they could all be defined from within Blender. We also used Blender scripting to generate some of those gameplay objects ahead of time. Shown here is a snippet of a script that we used to generate the colliders from the environment model. And that's pretty much the extent of the customization we did for Flowerbed, but Blender gives you a lot of tools and extensions to make custom behaviors for your own experiences, such as object linking and modifiers. And the scripting is very powerful, so you really can make your own sophisticated tooling on top of Blender if you need to. So, all right. After that, we were able to export the GLTFs from Blender and import them directly into Three.js. So that's that, right? Well, there's a bit more work to do. We still had to compress everything. Compress the GLTFs, then compress the textures, then make the KTX2 textures like we said everyone should do. For Project Flowerbed, we were looking at almost 700 megabytes of uncompressed models and textures alone, which is a lot to load on the web. Fortunately, there are tools to do all that compression and more. The ones we looked at are GLTF Transform and GLTF Pack. They are both open source command line tools that let you do extra processing on your GLTFs and textures, and handle everything that we've covered so far. We primarily used GLTF Transform for Project Flowerbed, but they both support a wide variety of workflows. Those tools take in a GLTF and produce a GLTF that has been compressed or has had unused nodes removed or any other processing you need. And that GLTF can then still be loaded in Three.js or any other web engine. However, since many of those compression schemes involve GLTF extensions, you have to be careful to make sure that you enable support within those engines for those compression extensions. KTX2 and GLTF compression is fortunately well supported, so getting them to work in Three.js was a matter of adding a few functions to turn on that support. At any rate, for Project Flowerbed, our model asset pipeline now looked like this. We wrote the pipeline that used GLTF Transform to quantize the meshes, compress them, convert textures to KTX2, resize large textures to further reduce file size. It was another step in the middle, but we found it well worth it. Having a programmatic content processing pipeline meant that we could run it and reprocess our GLTFs on demand and recreate them whenever we made changes, either to the models or to the pipeline itself. It let us fix bugs in our pipeline, fine-tune our compression settings, and automatically export all of our models to capture those changes whenever we updated them. And also, it was valuable for the file size and runtime memory savings. Let's take this rabbit model, just one of many in Project Flowerbed. The version that we exported straight from Blender was 4.1 megabytes, and running it through our processing and compression script brought it down to 2.3 megabytes, almost half the size. Now apply that through every single model, some more compressible than others, and we were able to shrink our whole bundle from the almost 700 megabytes to less than 200 megabytes. Still big, but much more reasonable for a full 3D web experience. Now, that pretty much covers all the visuals in the experience, but there is still all the audio. And audio is important. Having good sounds can make your experience that much more immersive. Like with models, we needed to figure out what file format to store our audio in. Browsers historically tended to have incomplete audio format support, forcing developers to include different formats for them to play on different browsers, but fortunately that's mostly no longer the case. We use the WebM format, which is an open format for both audio and video, and enjoys widespread support on most modern browsers. You can create WebM files from WAV or MP3 files. We created a command line-based pipeline for that in Project Flowerbed to automatically compress and process our audio, like we did for the models. As for playing the sounds, modern browsers all implement the Web Audio API, which lets you play audio and gives you lots of fine-grained control over a sound's parameters, like the gain and the panning. However, it is fairly low level, so like with visuals, you can build them on top of an engine. There are a number of sound engines available, and some of the 3D engines like Three.js have their own sound components to work with the visual part. One of the most powerful features of web audio is that you can use it to create fairly immersive audio. By manipulating the Web Audio API directly, we were able to add filters, change gain, and apply various effects to our sounds. It also supports positional audio, which let us define both the listener and the sounds themselves in 3D space, which is very handy in VR. And finally, there are a few libraries that support ambisonic audio, which is a full sphere surround sound format. We didn't use ambisonic audio for Flowerbed, opting for stereo positional audio, but ambisonics can be very powerful in VR, especially for immersive videos. So now we've got visuals and we have audio, and it's time to put it all together. And now it's back to Scott, who will talk about the tooling that makes the development process a lot more pleasant.
My absolute favorite thing about building WebXR apps is the fantastic set of dev tools that make it really easy to understand what an app is doing and how it's performing. First of all, you can use Chrome DevTools remotely to learn all kinds of stuff about your app as it's running on your headset. By opening up Chrome's device inspector on your desktop machine, you can attach over ADB to a browser instance running on your Meta headset. After connecting, you can debug your running app, view your console output, see things like GL errors, and even track asset loading over the network. The dev tools also have awesome CPU and memory profilers that let us capture and analyze data from our app to understand our resource usage and performance and find targets for optimization. You can see here how I recorded a few seconds of data from Project Flowerbed. And now I can click into a frame and drill down into the stack to see the runtime cost of different functions. Remote Chrome DevTools are a great way to understand what the app is doing on your headset. But if you don't have a headset handy, the WebXR emulator plugin is a useful tool which lets you emulate a WebXR device on your desktop browser. Most of our developers use both the emulator as well as their headsets when working on Project Flowerbed. The emulator is great for quick iteration without needing to take a headset on and off, or just for situations where you don't have a headset ready. It's just another nice tool in the WebXR toolbox. Along with the awesome browser-side tooling, MetaQuest browser developers are also lucky enough to be able to use many of the great Oculus developer tools. For Project Flowerbed, we use the Oculus Developer Hub to continually monitor performance and resource usage, as well as to easily send ourselves URLs to view on headset. The Metrics HUD and OVR GPU profiler tools also work with immersive WebXR and are a great way to always have an eye on performance. If you want to learn more about these core Oculus performance monitoring tools, check out Jimmy Lee's Performance and Optimization on MetaQuest Platform talk, which is available on demand now. Finally, my absolute favorite developer tool is RenderDoc for Oculus. RenderDoc is fully functional with 3D web content and lets us capture, replay, and debug scenes on the GPU just like it does with native apps. The capture replays show us exactly what the GPU is doing, step by step, and lets us see exactly how our scene gets rendered. We can get hardware performance metrics from a replay to understand the GPU performance of our scene and find good candidates for GPU optimizations. RenderDoc also has viewers for all the data associated with every draw call it captures. It even lets us edit shaders within a replay and immediately see the results of those edits. I cannot recommend it highly enough, and I encourage everyone to incorporate it into their development workflow. Let's talk about performance a little bit more. Performance is critical for every VR app. The web shares the same performance constraints as native apps and has a few new ones. The same general performance tips for native apps apply to the web. Minimize your overdraw, avoid using expensive post-process effects, and use LODs and bitmaps where appropriate. Fortunately, most of the performance-focused Oculus platform features work in WebXR, including time warp, fixed foveated rendering, and phase sync. The web has a higher per-call cost for GL functions such as state changes and draw calls, so it's critical to use features like multi-view and instancing to minimize the number of GL commands you call each frame. All of the WebXR engines provide access to these features, but you need to make sure your content is using them. I feel strongly that one of the most valuable things anyone can add to their development process is to regularly use profiling tools to understand their application's behavior. Tools like RenderDoc make it easy to profile your application, understand your performance bottlenecks, and find optimization opportunities. By profiling your application on a regular basis, you won't just get better performance, you'll get a deeper understanding of what your app is doing and where to focus your effort. Good profiling tools are an amazing way to understand your application and provide a consistent path to significantly improve your performance and quality. Be sure to check out Dave Hill's WebXR development and optimization talk from last year's Connect to learn more about optimizing the performance of your WebXR app. I hope we've given everyone some solid direction on how to make amazing WebXR experiences. The thing I love most about building for the web is how easy it is to jump in and start creating fantastic things. And I hope everyone who's been watching today is excited to grab some of these tools and start building their own WebXR apps. Please go check out Project Flowerbed and keep an eye out over the next few months as we publish more learning materials and guides that will explore deeper into how we built it. Thanks for watching.